This video describes the results of an experiment using trajectory clusters to determine if there are any long-term climate trends evident from a trajectory climatology. The underlying assumption is that a flow-based kinematic trajectory can represent air mass movements and their persistence. The results presented here summarize the cluster analysis for each of 7 decades of trajectories from 612 locations evenly spread over the globe. The tables and graphics are pre-computed. More detailed information about the trajectory and clustering computation is available on the Cluster Climatology webpage. If you don't know how trajectory clustering works, follow the modified link to take you to the page describing the clustering process. The trajectory and clustering computations were done independently for each of the 612 locations, which can be accessed by entering a latitude and longitude. But which locations would be of the most interest? In addition to cluster persistence, which is defined as the number of sequential trajectories expressed as hours that stayed in the same cluster, or in other words, had the same upwind origin. Each trajectory point was also tagged with the ambient temperature and pressure. A linear regression slope for each of these variables over the 7.5 decades was computed for every location. And these are the plots shown on this page. With respect to cluster duration, there is no obvious global trend. The largest changes in duration, both positive and negative, are centered over the tropical regions, with many of these locations adjacent to each other. With respect to the origin point temperature, the origin point being defined as the starting location of the backward trajectory calculation, the overall global temperature trend is positive, with some of the largest positive changes in the southern hemisphere. There is a hint of a few stable or slightly cooler regions closer to Antarctica. Because the trajectories all originated at 1,500 meters above ground level, temperature changes are expected to be more damped compared to those at the surface. The last global graphic shows the change in the atmospheric pressure at the trajectory origin point. Changes to atmospheric pressure at 1,500 meters represents changes in the mass of the atmosphere above that level. Because the pressure value represents a layer average, it may be a more reliable indicator of climate change than temperature at just one level. The graphic indicates the globe is dominated by increasing pressure and therefore temperature. However, there is a large region of decreasing pressure across the Southern Ocean and along the Antarctica coastline that was barely noticeable in the temperature graphic. The previous graphics showing average trends in temperature and pressure could have been generated without the use of trajectories because they were all computed at a fixed location. They are shown here to determine if there are any obvious locations that might require a more detailed examination. For example, if we sort the decadal trend data by trajectory cluster, it might reveal some relationships that were hidden when the average consisted of data from all wind directions. Go ahead and press the Click Here button. If we just take a closer look at the default location used in many different high-split trajectory examples, 40 north, 90 west, the global plots look rather uninteresting at that location. For duration, temperature, or pressure. Press the Update button, and the trend graphic at the top next to the position entry shows a lot of variability in duration, the green color, little trend in pressure, the blue color, and a slight positive trend in temperature, the red color, even though the values are averaged over all the clusters. If we scroll through each decadal cluster to find the most frequent one in each decade, for the 1950s, the 1960s, the 1970s, the 1980s, and in the 1990s, no direction seems dominant. The 2000s, the 2010s, and finally the 2020s, the short decade. We can see that in every decade, except the 1990s, the slower trajectory cluster from the northwest sector was the dominant one. Note that the northwest sector is not always identified by the same cluster ID number. The clusters for each decade are computed independently. If we organize these results in a simple table showing the dominant cluster results by decade, the 1990s seem to be the dividing decade. The averages, shown at the bottom in red, comparing before and after the 1990s, show an increase in the frequency, cluster duration, temperature, and pressure. I don't know if any of this is significant or that this is the ideal location to detect changes, as the selection of this site was just for illustration purposes. Other locations may show different results. The basis behind the clustering approach was to see if it could be used to segregate climate data into subsets with less variability. The success of this approach may be very dependent upon location, and there are another 611 locations that could be examined in more detail.